tracer diagnostics that of this type that have never been run before. I mean, it's an impressive project. So this was done in collaboration with RESMAN Energy technology and obviously Utah Forge. And the advanced tracer interpretation resulted in about 20 different deliverables. And several of them are very novel. And we're slowly, giving this out into the public and getting this published.
Welcome to Geothermal Unleashed, where we're going to explore the cutting edge of geothermal energy. I'm Elizabeth Cambry from the Ballarat New Energies team, and I'm here to help educate and document geothermal's rise in the global energy transition. Joining me today is Chris Fred, who's a co-founder and partner of Blue Angel Energy, where he partners with technology providers to help accelerate the commercialization of their technology into different markets. Chris, so we first met, I believe it was in Qatar, maybe almost a decade ago. And so you bring a wealth of knowledge from international locations in the oil and gas industry. And so now you've got the opportunity to take some of your expertise and bring that into the geothermal space. So we're going to be touching on what you're doing in the geothermal sector today, and I'm very excited about our conversation. But I would like to start by first asking you to walk us through your career, your experience working with Schlumberger in both Russia and the Middle East, and what you were focused on.
Well, yeah, first of all, thank you for inviting me to participate in this Geothermal Unleashed podcast. It's a pleasure to be here. So my 22-year career with Schlumberger included about 12 years working internationally in Russia and the Middle East. And that was bookended by about 10 years in the United States. I had the opportunity to be in a variety of roles across 4 different business segments. And there I gained experience in hydraulic fracturing, production optimization, technology integration, and new product development. And I think it's interesting to note that this experience, it spans a wide range of reservoir types, including shale gas and shale oil, tight sandstones, carbonates, volcanics, and even fractured basement reservoirs. So a lot of that is relevant for EGS applications in granite formation, so bringing a lot of different reservoir characteristics all together. In my role as a global business development manager with Schlumberger, I helped start up a new consulting business. And that was focused on assisting operators in evaluating unconventional resource opportunities and driving down the unit cost of energy. And had the opportunity to lead several due diligence evaluations to support investment decisions and accelerate commercial viability of assets. So it's a blend of, kind of technical and commercial experience that I think brings a unique perspective to addressing challenges in a variety of reservoir conditions.
Okay, excellent. So before we talk about what you're doing with Blue Angel Energy, you also are currently a part of Solve E, or is it just Solve Global Technologies?
Solve with a capital E.
With a capital
E for energy.
Okay, perfect. So why don't you hit on what you're doing with them before we dive into Blue Angel Energy?
Yeah, certainly. So I was getting several requests for organizations to help with product development. Basically to bridge the gap between technology and practical application. So I founded Solve to really assist in technology acceleration, if you will. Lots of examples in kind of tailoring products for different reservoir applications. But I think an interesting one to talk about is helping an engineering organization in Australia with transformation. And this was particularly rewarding because it involved aligning several different business groups, which were originally independent companies, and helping them align with the executive team under a fit-for-purpose product development process. So this was about a 14-month engagement where I helped them establish a process that aligned with their needs, and then implemented it across various projects, including water management, emissions reduction, Internet of Things, and helping build a portfolio of project pipeline that applied to energy and in the mining sector. So really interesting opportunity to transform an organization and their technology portfolio.
Really exciting. Okay, so let's turn to Blue Angel Energy. So you're working with different startup companies. Can you talk a little bit about those companies that you're working with?
Yeah, certainly. As you mentioned, Blue Angel is a technology accelerator, really helping advance innovation in the energy sector. And we've had the opportunity to work with some really exciting companies. A couple of examples. One is a startup company that's developed a novel displacement pump technology, completely different approach to pumping fluids, and it's agnostic to the power source, and it significantly reduces the cost of ownership. Another one is a startup company that's developed a high torque drilling transmission, and that's currently undergoing field trials. And then we've been working quite closely with RESMAN Energy technology. That's a privately held Norwegian company, and they specialize in tracer technology for reservoir surveillance. And we've had the opportunity to collaborate together on advanced tracer interpretation for enhanced geothermal systems. So it's interesting that all of these three examples, these technology are all relevant in the geothermal space. So it's interesting to kind of see how these all play together.
So I'm just curious for my own understanding. So the part that you're playing, are you coming in helping these companies position themselves with the proper value proposition, helping them get the field trial, and then apply their technology and find their growth in different markets?
Yeah, all of the above, right? So we fill the gaps in their organization. So, for example, the pump technology, they've done a great job with the engineering, the R&D, in a prototype that's been in the field in field tests, and we're helping them to find a manufacturing partner to bring it into the U.S. The drilling company it was started from ground zero. We actually provided them with seed money, built some IP portfolio around it, and helped them develop the technology that's now in field trial. So it's anything and everything, but we're myself and the partners, we cover a broad spectrum of the disciplines in oil and gas. So we're leveraging a broad technical background with our commercial experience to help fill gaps, if you will, in organizations.
Okay. All right. So I'm very excited for the conversation we're going to have on RESMAN and that project within Forge. But I want to ask, you've got a fabulous background with oil and gas that spans, all over the globe. How did you familiarize yourself with geothermal?
Well, my understanding with EGS particularly comes from really a combination of hands-on experience and my background in oil and gas, which is directly applicable.
Okay.
Working on the Utah Forge project with RESMAN has really been focused on advanced tracer interpretation that has provided valuable insights on what drives the performance of geothermal systems. So I think that hands-on aspect is really important. Go ahead.
Did you have any geothermal exposure prior to Forge?
No, nothing prior to Forge.
Okay.
Yeah, I've also been attending, different industry events in geothermal. One example is the Geothermal Rising event in Rio, where you were one of the committee members a few months ago. And that's really, nice opportunity to establish cross-discipline knowledge sharing. And that was really one of the topics of one of the breakout sessions in that event. And it reminds me of the early days of the Barnett Shale and how shale gas started up. And that involved bringing a lot of multidisciplinary teams together to really establish optimization for horizontal drilling and multi-stage fracturing. And initially, those teams really struggled to communicate. They used different terminologies. They didn't understand each other's objectives, which isn't surprising, right? They came from siloed organizations and now forced to work together in a different way. But as they learned and as the knowledge was shared across the disciplines, they aligned on key performance drivers for the asset. And that really caused a culture of innovation and continuous improvement to really develop. And you really knew when the teams were evolving, when the geologist would talk about frac gradient and the frac engineer would talk about drilling ROP. And I think, there's an excellent opportunity for the geothermal industry to do something similar. And I think they should really make it an intentional objective to drive diverse disciplines together.
Yeah. Okay, so let's turn to talk about specifically what you worked on within Forge. And I just want to say, I saw one of your presentations back at the conference in Reno last year, and I thought, I never anticipated that a presentation on tracers would paint such a fantastic story about what was happening at Forge in terms of the fracture connectivity. There's so much information that you're able to pull. So I really appreciated that presentation. So I wanted to dive in and talk a little bit about it. So do you just want to give a background on what you're doing within Forge?
Yeah, certainly. Now it's been a very exciting project, right? It's very data rich, which obviously bringing together a lot of different measurements across microseismic, fiber optic, the treating pressure data, et cetera, with tracer diagnostics that of this type that have never been run before. I mean, it's an impressive project. So this was done in collaboration with RESMAN Energy technology and obviously Utah Forge. And the advanced tracer interpretation resulted in about 20 different deliverables, and several of them are very novel. And we're slowly, giving this out into the public and getting this published. But I think it was interesting. I presented this to several operators, and one of them described the analysis as going 3 levels beyond normal tracer results. And to kind of put that in perspective, it's typical that someone will receive a spreadsheet of tracer concentrations showing stage contribution. And then you're left to kind of figure out what all that information means. We actually took it to the point where we're characterizing the flow paths and establishing, how that relates to relative design parameters in the system. And maybe we just talk about a couple of the key outputs. Yeah. One's the quantitative production log. We call it QPL. And the other fracture circulation volume. So QPL, or quantitative production log, that's the percent flow contribution from the flow paths per frac treatment stage. So we get resolution of each of the stages and what they're doing over time. And that's with undisturbed flow. It's not, there's no intervention with a mechanical log. This is undisturbed flow that we can evaluate performance over time. So each new sample, right, from the production stream, that provides a new QPL at that point in time. The fracture circulation volume, that's derived from the tracer resonance time distribution. And when we combine that with the QPL, we're able to provide a lot of unique characterization of the flow paths. And one example result is the first known measurement of the effective porosity in a proppant flow path in the subsurface. And it's revealing remarkably high effective porosity of about 80%. And if you compare that to conventional proppant packs, which is about 35%, or even laboratory measurements with partial monolayer coverage around 60%, it's significant, right? I mean, that's a very different type of propped environment than we're thinking about with a typical frac treatment. So there could be lots of mechanisms for this, right? Asperity, surface roughness in the system can cause arch formation, local screen outs, local channeling. Natural fractures can be contributing to this, or a combination of any of those things, right? But the point is that this knowledge that the flow path is very different than what we classically think of means we have new ways to think about optimizing it. And it's something that, this actual flow path in the subsurface that we're seeing, it's not predicted by current models. So it's an opportunity to really think outside of the box and approach this differently.
Okay, interesting. Okay. So I have questions on that, but before I dive into that, I want to ask, so what were all of the designs of the frac job that you're able to potentially optimize that you can see with the tracer data? So you mentioned effective porosity. What else?
Yeah, so what maybe we look at the design parameters that were changed in Utah Forge. Okay. So they varied the type of fracturing fluid from slick water to cross-link CMHBG, so a viscous fracturing fluid. They varied the number of clusters per stage. They had challenges in placing proppant in some of the stages. So obviously we've got stages that did or didn't get propped effectively.
Okay.
So there's a wide range of variability in the type of treatments that were pumped from stage to stage. So from the tracer interpretation, we get a lot of characteristics of that. And we integrated that tracer interpretation with estimates of the economic life for each of the stage, where we leverage the Gringarten's thermal decline curves. And by that, we're now able to couple all those design parameters with economic performance and predict what it's going to look like in the future. And this approach allowed us to quantify, commercial impact of things like the number of clusters per stage, the proppant loading, which well got fractured and propped versus, whether it's the producer or the injector. And it's really pointing us in some interesting directions of things to consider for design enhancements.
Okay, so when you say the economics, are you saying you can look at like the temperature degradation of that fracture? Is that what we're ultimately looking at to look at the lifespan of the fracture?
Yeah, so the Gringarten thermal decline curves, key inputs into that are the flow rate per fracture and the surface area per fracture that's contributing to enthalpy extraction. And those are generally not well known. We can run a production log and we get the flow rate per fracture, but to date, we don't have any real measurement of the surface area. So by integrating the data in Forge, we're able to get both of those variables as a function of time. And that's direct input in Gringarten. So we can then use the dimensionless time and dimensionless temperature, picking an economic limit for the system and predict which stage is contributing the best. So ultimately, we've accelerated the learning curve, right? We don't have to wait 2 to 3 years to look at thermal decline while circulating. From a couple of week circulation test, we can predict the thermal life of the system using Gringarten's equations. So we can react quickly to which design is working and which one's not.
Cool. Okay, so just for my frac background, what was the best type of frac fluid based on the tracer results?
Yeah, so the interesting thing that seems to be standing out is proppant transport and proppant placement is important.
Okay.
So we did see some differences in CMHPG versus slick water. So we're estimating about a 17% higher conductivity in the system with CMHPG. So it looks like we're getting better transport into the system. There's also some questions about what that does to the near wellbore tortuosity and hence parasitic losses in the system. So first impressions, the viscous fluids seem to be providing some benefits, but obviously all the economics of that have to be weighed out.
Yes.
But proppant transport looks extremely important.
And was the high viscosity friction reducer also a frac fluid that was evaluated?
I can't recall exactly what they ran for the friction reducers, but in general, we're talking about slick water on the order of a centipoise versus a cross-linked fluid that started out at maybe a couple hundred centipoise and very quickly broke to 1 centipoise at 430 degrees. So in the far field, yeah, both treatment fluids look fairly similar. In the near wellbore, there's a difference in viscosity.
Okay, so we get these results. Now, what are we doing with them? Is there opportunities to do more stages to further optimize and use one particular frac fluid, or is it being adopted in the industry?
Yeah, I think the industry is still, absorbing and understanding what all of this means, right? There's a lot of variables, lots of parameters, and clearly we don't have all the answers today. There's lots of open-ended questions that more science will bring value, and hence, that's the reason why we're doing research projects like Utah Forge. So yeah, we have a lot to learn. I think if we put it in perspective, the lessons learned from shale gas and shale oil, right? Horizontal wells, multi-stage fracturing, that is a great place to start. Those wells were designed to perform in nanodarcy rock where we have low flow rates. And obviously, we're targeting, higher flow rates. We're targeting low pressure drops to make sure that we don't have parasitic losses for EGS. And it's important to put that in perspective, right? If we look at tight gas sands where we spot frac all the time with very different treatment designs, cross-linked fluids, high proppant concentrations, very different perforation strategies. So what we do in slickwater type of treatments in shale gas isn't the only option we have as an industry. We've done lots of different things. So, I think it's a really big opportunity for us to tailor a solution specifically for EGS. And that's where I think there's a lot of open questions about what is the optimal design and how do we get to that approach as quickly as possible.
Now, when you look at what happened with the shale revolution, we turned to these cookie cutter frac recipes. You just said we need to tailor for EGS, but do you think then we find an optimal solution and then we need to kind of go that cookie cutter route? Or are we going to have to really do a lot of engineering for each individual well?
No, I think we're going to evolve to the optimal type of design for EGS.
Okay.
And whether that looks the same as what we do today in shale or tight gas or something very different, that's something that as an industry we'll learn. But yeah, I would envision that once we find what that answer is, we'll focus in on that as kind of a standard approach.
So one thing that I think is so interesting about your background is that you have worked on so many different types of reservoirs and you've been exposed to hydraulically fracturing different types of reservoirs. And so you have more technology that you've deployed under your belt. So I'm curious, aside from plug and perf, could next generation geothermal benefit from technology that's used to complete wells, say in the Middle East, like inflow control devices or sliding sleeve technology?
Yeah, interesting question. So I think with most technologies, right, there's pros and cons to consider. Maybe if we start with plug and perf, those operations are known for being efficient and cost effective in creating a lot of fractures along a well. But obviously there's drawbacks, right? Such as over displacement during pumping down of plugs and guns, right? Non-uniform treatment of multiple clusters per stage. So there's lots of things that we take as part of the operations in shale gas that economically is performing, but may cause challenges for EGS. So as an example, right? The experience in shale gas is that over displacement has an insignificant effect. In those situations, we're pumping, generally smaller sand sizes. We know that duning effects can have a role, and in that environment, over displacement doesn't appear to be critical. The question becomes, with different objectives for EGS, what is the impact of over displacement there? I think it's something we need to think about and look at. Another example is that we've got indications that the more economical stages are ones with fewer clusters per stage from a Greengarten equation perspective. Obviously, that competes with operational efficiency and the cost of developing the assets. So there's probably going to be a new optimum in terms of the number of clusters per stage that balances, performance of EGS versus operational efficiency. So lots of things like that we kind of take for granted today as the direction we want to go for shale gas. But I really think the requirements of EGS will result in a different optimal that we'll narrow down to.
Okay. Are diverters used in EGS today?
Today, I'm not aware of diverters being used, but I think certainly there's opportunities there.
Yeah.
And you had mentioned sliding sleeves, right?
Yeah.
I think those certainly bring value in mitigating over displacement, and also they offer a larger cross-sectional flow to area for reservoir connection. So when I think about parasitic losses on the near wellbore, sliding sleeves with open connections make some sense. And there's lots of different variants that allow you to close off the sleeve or activate ICDs later in the life of the well. So these are all things that look interesting and promising for EGS applications. I think as an industry, we just have to evaluate the cost benefits of those type of solutions.
Yeah. Yes, economics are extremely important. Okay, so can you clarify for me where is the forge like the efforts that you're working on with Forge are, you've already completed a number of stages. Are there additional stages or wells that are being drilled that are in the future?
Yeah, I think at this point, that's something the Forge team will announce what their plans are. I know that there's lots of things being discussed in terms of what to do next and what brings the most value in terms of knowledge development. But yeah, I think we'll see some exciting announcements from the Utah Forge team in the
I like
near
to hear
future.
that. All right. Well, to wrap things up, what do you see, or what are you most excited about for the future of next generation geothermal?
Yeah, for me, I think there's an opportunity for everyone to learn, right? I think that we've got a good starting point with horizontal drilling and multi-stage fracturing that's proven the feasibility of EGS. Now we're on the path to optimizing that and turning it into a successful commercial venture, right? But in the process of that, we're learning things, and I really think a lot of what we're learning in EGS is going to translate to lessons learned back to oil and gas. And examples of that, some of the signatures we're seeing in the tracer data for Utah Forge look very similar to published results in places like the Permian Basin and the Bakken. So we know that these slick water type of treatments, the characteristics of the flow paths probably are very similar across the different reservoir types that we're dealing with. So again, I think it's going to change everyone's perspective on what is the optimal solution. And we're balancing lots of factors. So for example, we're balancing the number of clusters per stage for operational efficiency versus the risk of what that stage looks like over the long term for EGS, right? The risk of things like short circuits, et cetera. We're balancing proppant transport and hydraulic fracture conductivity and what that means for fluid viscosity requirements versus parasitic losses over the life of the project. And we're balancing well construction costs and design changes versus what may be required in the future for intervention, maybe shutting off zones or refracturing or drilling replacement wells. So there's a completely new dynamic in terms of what we think about now, I think, for the life of an EGS well. And I'm confident that multidisciplinary collaboration is really going to lead to a lot of innovative solutions and a lot of success for next generation geothermal systems. I think we simply need to think about it from a different perspective.
Love that. Well, you make it sound so exciting. There's so much opportunity within the geothermal space, and it's very exciting that there's a lot of engineering that needs to happen in optimization. It makes it more fun. Well, Chris, I want to thank you for joining me today, and I want to thank all of our listeners for joining us on this episode of Geothermal Unleashed. I hope today's discussion has sparked new insights and deepened your understanding of the geothermal industry's incredible potential. Until next time, keep pushing the boundaries of what's possible, and let's continue working together to unleash the full potential of geothermal. Thank you.
Thank you.